Assalamualaikum warahmatullahi wabarakatuh, and a very good morning. So, can you guys hear me? Sound check. Someone please respond. Okay, good. Okay, so today we're going to continue this topic, which is the inverse exact transform. And actually, it's not only for the inverse exact transform. So actually, this topic is for both forward and inverse. Okay, because what is the basic? The basic is we're going to do the solution based on tables. Okay, so far we have seen one type of table. So this is what we call a Z transform pair table. Okay, so we have 1, 2, 3, 4, 5, 6 up to 13 items or 13 pairs that we can use to facilitate us so that we can do the solution easier. So it doesn't have to do the Z transform formulation, the math. So that one is a bit complicated. So we use this table. Okay, we use this table. But to do this, we need to make sure that we get into this form. Okay, so we need to have these forms. So whatever the equation that you have, you need to make sure that you are converting it into this form. So you need to find out. So you need to manipulate the equation so that it becomes one of these forms. Okay, so we have seen several examples last time in our last class, and what we should do is actually this one, which is a partial fraction expansion, because we want to convert whatever we have into the forms that we have in the table. So that's why we need a partial fraction expansion. And another one is we need to do sometimes we need to do a long division. Okay. In some cases, we need to do a long division where normally this is when you have an n greater than m. And what is the n and m? N and m is actually the power. Okay, the power of the n is the power of the denominator, and m is the highest power of the numerator. Okay, so today, we're going to look at another table, which is what we call a Z transform properties table. Okay, so we have how many properties? 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 properties. And the simple purpose, so we're going to use this actually, these properties, so that we can do the forward or inverse Z transform easier, rather than using the original equation of the forward and inverse Z transform. So now we have 2 tables. One is a Z transform pair tables. The first one, the one that we have covered last Tuesday. So, and this is another one, which is what we call a Z transform properties table. Okay, so we're going to look at example of these properties. So we're going to look at linearity, time shifting, scaling. We're going to skip time reversal, differentiation. We're going to skip that also. Conjugation, we're going to skip that also. So, and then we're going for example for convolution. So we're going to look at linearity, time shifting, scaling, and convolution. Okay, so because those are the properties that most of the time we're going to use it. So we're going to use all these 1, 2, 3, like linearity, time shifting, scaling, and convolution many times. Okay, so in our next chapters and next classes. Okay, so because when analyzing, when designing, so we need those things. So time reversal, differentiation, conjugation, initial value theorem, that one is a bit, it's quite rare that we're going to use those properties. Okay, so let's go to the first example for today's, which is example 7. So this is from a linearity properties. So how can we use this so that we can do a forward or inverse Z transform easier compared to solving the original equation of the Z transform. So let's say we have actually this is the property. So this is the rules. If you have an alpha h1n, so this is the first. Let's say we have a 2 impulse response. So this is a 2 impulse response. So h1n is the first impulse response. Second one is the second impulse response. So means that we have 2 systems. Okay, so what is an impulse response? Impulse response is a representation for a system. So when you have a H1n and H2n, so you have actually a two system. And this two system is combined into a single system. Okay, so actually we have a one system, one big system. So it consists of two systems. So maybe a two subsystem. So which is one of it is a H1n, another one is a H2n. And what is alpha? Alpha is just a multiplier, a weight. Sometimes we call it a weight multiplier. This is a multiplier for the second system. So if we have this, so actually the Z domain will be, if this is H1n, so we will have H1Z. Okay, that one is a straightforward. And this is multiply, so you just do multiply. And this is plus, you just do plus. Because this is a linearity property, so it will be a straightforward. This one is a very straightforward. But the ROC, okay, the ROC is actually the ROC of H1 because this is a two system. So it has a two ROC. So each one has ROC, its own ROC. So what we have here is you need to do a union between these two ROC. Okay, so let's see one example. So let's say we have a Hn equals to negative 1 over 2 to the power of n un plus 2 1 over 3 to the power of n un. Okay, so, and we know that these two is actually a causal, right? So this is causal because this is un. Un is the n start from 0 up to infinity. So there is no value, the amplitude value for n less than 0. So then this is actually causal, and this is also causal. So the solution is we can check this. We can check this using our table. Okay, so actually this is let's see which table this is. The one may table number 4, if I'm not mistaken. Table number 5. Okay, table number 5. If you have en un, so you should get 1 over 1 minus ez to the power of minus 1, where z greater than a. So means that this is for a causal system. So then this is where you will have a 1 over 1 plus 1 over 2, because this is minus 1 over 2. So this is actually minus 1 over 2. So plus 1 over 2. And this is another one, so which is, this is 2 because this is a multiplier. So this is 2. And then this is the 1 over 3 here. So straightforward, you just use pair number 5. Okay. So this is what we have, but we have the ROC for this one, z greater than 1 over 2. And this one, the ROC is z greater than 1 over 3. So we need to combine this ROC because we cannot have two separate ROC. So as a single system, so you should have one ROC. So because the ROC is actually a union of ROC1 and ROC2, so this is where we will get, because if we sketch, so 1 over 3 is supposed to be somewhere here. 1 over 2. Sorry, this is not union. This is a cross section. Okay, so the first one is you're going to have, so 1 over 3 is somewhere from here going up. Okay, going the outer ring, and this is 1 over 2. So which area which is overlap, so that will be your final ROC. Okay, so only 1 over 2, z greater than 1 over 2. So those are actually the overlap region of these two ROC. So this is what it means by this equation. Okay, so then what is the ROC for Hz? The ROC is z greater than 1 over 2. So because that's actually the ROC H1, and then you have this symbol ROC H2. Okay, find the overlap region. Okay, this is another example, example 8. So let's say we have a Hn equals to 3 delta n minus 1. plus 2 1 over 2 to the power of n u minus n minus 1. Okay, so then we know that this is non-causal. Okay, because this is a u minus n minus 1 is you will have something like it start with -1 up to minus infinity. Okay, so this is actually u minus n minus 1. So we have a hn, which is the range from minus infinity up to minus 1, which is hn is not 0 for n less than 0. So it is non-causal. And this is actually just one sample, so it doesn't matter. So this is the one that's when we look at this one, so it is actually non-causal. So what is the solution? The solution, you can do that. So this is actually just checking a pair number 4. So this is pair number 4. This is pair number 4. So whenever you have a delta n minus m, so you should have a z to the power of minus that n. Okay. So that's why we have this is a n minus 1. So you have a z to the power of minus 1. And this is 2 1 over 2 n. And because this is non-causal, this is from pair number 6. So this is pair number 6. Okay, so you should get this one, but the ROC is a z greater than z less than alpha. So then, so what we'll have is this is a 2 over, because we have 2 here, and then this is 1 over 2. So this is 1 over 2, and the ROC is a z less than 1 over 2. So what are the region which is overlap between the z greater than 0 and a z less than 1 over 2? So the overlap region is actually a 0 up to 1 over 2. Okay, because this is greater, so this is less than. And because we have this less than, so it is obviously then we prove that actually this is non-causal, right? So actually this equation, the Hz equation, is a straightforward, but you need to be careful on the ROC because we are combining the ROC. We need to find the overlap region of the ROC. So okay, so this is the second properties that we're going to look at. So we call it a time shifting. Okay, so why it is a time shifting? Because if you have an impulse response which is delayed by some samples, some delay sample time, so then the z domain will be, if this is hn, you get hz. If you have a delay, so you're going to have, you need to multiply with z to the power of that delay. Okay, so this one. So this is the delay. So your hz should be multiplied with z to the power of minus of that delay. So let's see. So we have one example here. hn equals to delta n minus 3 plus to the power of n minus 2 u minus un minus 2. Okay, so actually if there is no delay, this term, so actually we should have, we can have, if there is no delay, so it's supposed to be u 2 to the power of n un. So this is where you're going to use pair number 4. Okay, pair number 4, this one. This pair number 4. So, but because we have a delay, so it's not enough just to use pair number 5. It's not enough to use only pair number 5. So you need to combine this pair number 5 with these properties. Okay, so this is an item, a properties from a properties table. So we combine both. So if it is no delay, so we already know that this is actually just 1 over 1 minus 2z minus 1. Okay, so this is what we have. So, but because there is a delay, because how do we know it has a delay? Because this is hn minus nd, so all the n, so we have n here, so we have another n here. So all these 2n are actually minus by 2. So it is delay by 2 samples. So then we know that we have a delay of 2. So delay by 2. So this is where you get 2n minus 2, un minus 2. Okay, then we can just straight use these properties, which is this one, this is your hz, so you need to multiply with z to the power of minus 2. Okay, so this one. So this is a z minus z to the power of the delay. Z to the power of the delay. So then this is delta n minus 3. So this one we get it from pair number 4. Pair number 4, the first table. So this is from the first table, pair number 4, straightforward. Not a problem, not new. So you just get a z to the power of minus 3. But this one, you suppose if there is no delay, it's a 1 over 1 minus 2 z minus 1. So which is this one. But then you need to multiply with z to the power of minus 2. Okay, this one. So because of this one. So it can be a very straightforward also. The solution is straightforward. And this is where still the same. So z greater than 2 because this is the alpha. So the alpha is 2. So then the z greater than 2. Okay, so that time shifting doesn't really actually change the ROC. And actually you can use this to solve the quick quiz. Okay, so you can use this to solve the quick quiz. Let's see another example on time shifting. Hn equals to 1 over 2 n minus 3 un minus 2. So now we have, this is a delay by 2, but this is something like minus 3. Okay, so but because if we want to have a delay of 2, so we need to modify this a bit. Okay, so how should we do that? So this is, we're going to manipulate this equation. Let's say Hn is equal to 1 over 2. This is n minus 3. So n minus 3 is actually n minus 2 minus 1. So now we have the same delay. This is minus 2. This is minus 2. Okay, and then expand that. So we know that 1 over 2 to the power of minus 1. So actually we can write it this way. This one. This is the same thing. Okay, so this is actually equal to 1 over 2 to the power of minus 1. So we bring that minus 1 out. And you have a 1 over 2 n minus 2, and this is n minus 2. So now we have the same delay. So now we have the same delay, then we can use the time shifting properties table. Okay, so and 1 over 2 to the power of minus 1 is simply equals to 2. So then you have this. And what is your alpha? Your alpha is 1 over 2. So then you can have, this is 2, 2 is here, and this is delay by 2, then you need to multiply by z to the power of minus 2. Okay, and your alpha is a 1 over 2, so this is 1 over 2. ROC is supposed to be z greater than 1 over 2. Okay, so this is actually not complete. So you need to complete it with ROC. Okay, this example is not complete. So there's some error there. So you should add ROC. ROC, which is a z greater than 1 over 2, because the alpha is 1 over 2. Okay, any questions so far? Because we have seen, I think, 4 examples before we move on. So anyone want to try to do the quick quiz again? So using this time shifting. So do you want to solve that? The time shifting. Okay, I will leave that so that one of you will get the bonus mark. Okay, so you can use this time shifting. So post your answer in WhatsApp. So it means that the bonus mark is still open. Okay, now let's see. After time shifting, so we're going to look at properties of a scaling. So this is what we call a scaling in Z domain. So where you have, let's say, if you have a e to the power of n hn, so actually the Z domain, so we're not going to do hz instead, so we're going to hz divide by that a. So if you have a to the power of n, okay, so you will do z divided by a. And what is the ROC? The ROC is you need to multiply the original ROC with a, right? With a. So let's see one example. So if we have Hn equals to Un, okay, let's see. So someone is maybe asking, Dr. S confirmation, the Z in ROC is always having modulus, right? Right, yes. Always have modulus for the ROC. Because the ROC is the Z again, so why it is have a modulus? So this is very important. Because what is a Z? Z is a complex value. Okay, so what is a Z? Z is actually a complex value. So that's why we have a real and imaginary. So in this plot, what is the Z? So we also say we also write it as a Z, 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 Z. But when we plot, there is no Z. So actually, the Z is complex value. So it is a combination of real and imaginary value. Okay, so Z is actually a real plus imaginary. So that's actually Z. So that's why we don't do this. We don't do a real plus imaginary. Instead, we write it as a HZ for a simple notation. Okay, for a simple notation, we just put it as a HZ because we already know that Z is a complex value. And that's why to better imagine this, so that's this is a Z. Z is on the horizontal axis, and this is HZ on the vertical axis. Okay, so whenever we have, so this is actually equals to H of real plus imaginary. Okay, so we need to understand that first. And when we draw ROC, so it is some region. Okay, and this is circular. It is based on radius, which is R. This is, let's say, alpha. So what is the R now? The R is alpha. Okay, but not just alpha. So it's supposed to be that one, or generally it is R must be some absolute value of Z. So because what is a Z? What is a R? R, trigonometry. Okay, another maths, trigonometry. So what is R? So you have your imaginary here. You have a real value here. So R is actually imaginary squared plus real squared, square root. Okay, so that is why R is actually Z with absolute value. What is absolute value here? Magnitude. What magnitude? Magnitude of imaginary and real. So that's why it always has that absolute value, because it is R. Okay, we are looking at the R. All right, so hopefully you understand this is what we call the anatomy of the Z domain. So because we need to look at poles and zeros, we need to look at the ROC always. R equals to, so that's why we always has this absolute value, because this is actually, if you doesn't want to put it as a Z greater than 2, so you can actually put it as a R greater than 2. Okay, and there's no, it's not possible that R is negative, because the lowest R is supposed to be 0. This is the lowest R, so there's no negative R. All right, so hopefully that's yes, this is actually quite important in understanding the concept of this Z plane, the complex plane, because we always put it as a Z, but when you have absolute value, you are actually referring to radius. Okay, so hopefully you see that it is very clear. So why it is a Z, why it is what is the complex value, what is the radius, What is later, we're going to look at what is the angle. It has a theta. We doesn't come to this yet. But later, yes, we need to look at this theta also. Okay, and this theta is very, very, very important. Okay. All right, so scaling in Z domain. So let's see one example. If Hn is equals to Un, so find H2n, where H2n is actually equals to 2 to the power of n Hn. So what does this mean? So this is actually, if you write it in full, so this is actually a 2 to the power of n Un. Okay, so actually we have we are already familiar with this form, because 2 to the power of 2 to the power of n Un. So actually we can refer that into to some table. This is pen number 5. Okay, you can do that, but we're going to look at it differently now, because if we know what is a Un, and actually we already know what is a Un. So Un, the Z is actually equals to 1 over 1 minus Z minus 1. Okay, so you can get that from the table, Un. This is pair number 2. Okay, so all right, let's continue. So let's say now this Un, so actually it is multiplied by 2 to the power of n, which is this one, a to the power of n, which is the a now is equals to 2. So for Hn equals to Un, so we already know it is a 1 over 1 minus Z minus 1. But when we actually multiply with a to the power of n, so actually we can manipulate this thing so that we don't do Hz, we replace the Z. We don't do Hz, we replace it with a Z divided by a. So in our case now the a is 2. So we do this. So H2Z is equals to Hz over 2. So everything, so this is Z, change this into, because we only have one Z here, so replace that Z with Z over 2. Okay, then you get 1 over 1 minus 2Z minus 1. But of course, this equation, this example, this is just to show the scaling properties. But when you solve this, you doesn't have to do this, because this is quite a long solution, because we already know that 2n Un is actually equals to 1 over 1 minus 2Z minus 1. So we can refer this to the table. And the Z is, the ROC is a Z greater than 2. Or in full, we should see this as an absolute value of Z greater than 2. Or radius greater than 2. Okay? So that's why sometimes in maths, you should you should say it in full so that you will understand. You say, okay, such this. Don't say Z greater than 2. Absolute value of 2. Okay, or what else? Magnitude of Z greater than 2. So that's what it means. That's what it means in our case. Or you can simplify it as the radius is actually greater than 2. Okay. Okay, this is another example on scaling. So Hn, let's see, we have equals to 2 to the power of n delta n plus delta n minus 1 plus delta n minus 2. And try to focus on this one, because in our quick quiz, so 3 of the answer is making a mistake with delta n. Okay, so try to focus on this one. Try to find out again what is the mistake, because the mistake is because of the delta n. All right, so let's continue. Hn equals to 2n delta n plus delta n minus 1 plus delta n minus 2. So what we have is actually, what is actually delta n? Delta n is just a signal with one sample. Okay, so this is actually delta n. And what is this? So this is delta n minus 1, which is, we have a delta n delay by one sample. So this is another signal, so which is, it's not at 0, but it is at 1. Okay, so this is actually delta n minus 1. And then, of course, this is another impulse, which is one sample. One sample is not located at 0, not at index 1, but at index 2. Just one sample. Okay, and if you imagine this signal and everything, so this is 1, 2, 3, 1, 2, 3, multiply by 2 to the power of n. Okay, so this one multiplied by 2 to the power of n. So what is the only sample that we have? The only sample that we have here is at n equals to 0. This is n, this is n. And because we are multiplying with 2 to the power of n, and the n is 0, so 2 to the power of 0 is actually 1. Okay, so this is actually you multiply with 2 to the power of 0. And this one, because we only have one sample at n equals to 1, so when the n is 1, so this actually becomes a 2 to the power of 1. So this is multiplied by 2. Okay, so actually this is equals to 1 multiplied by 1. And the other one, this is at n equals to 2. It is 1, and then you need to multiply with 2 to the power of 2, which is 4. Okay, so that's why if you look at this when we expand this equation, so it becomes something like this. So it is this one, I'll expand it first. So this is why this becomes delta n, because of this. Because at this position, so we have only 1. We multiply by 1 because this is 2 to the power of 0, 2 to the power of 0. So you get 1. The second one, so why this is 2? Because we have only one sample here, multiplied by 2 to the power of 1. And then the last one is why we get this 4, because of this. And this line is actually this signal plus this signal, so you need to plus and then plus. Okay, because this is plus, this is plus. All right, so make sure you can imagine the signal, this Hn, or the vector. To be accurate, actually this is not a signal. This is just a vector, and this vector is representing a system, which we call impulse response. So it's not accurate to say that this is a signal, because this is impulse response. So it's representing a system. If this is xn or yn, then we can call it as a signal. Okay, so if not, in general, everything we call it vector. Hn, xn, yn, those are vectors. Okay, what is a vectors? What a vector? Vector is a sequence of values, with index, right? With index. So then, so what we have here is, so then you can refer to table number 4. So refer to table number 4. Whenever you have delta with some delay, so you will get z to the power of that delay. Okay. Then go to this one. So this is where there's no delay here. So this is z to the power of minus 0 becomes 1. This is 2z minus 1 because the delay is 1. And then this is 2. The delay is 2. Then you have a z to the power of minus 2. So this is one solution. This is one of the, how do you solve it? And because this is math, so that's why sometimes math can be manipulated by several approach. Okay, so even in this case, we have 2 methods on solving it. And even in our quick quiz, the final answer, which is the Hn, we are finding the Hn. So you can have, because as I mentioned, you can have at least 3 different form of Hn. And all those 3 are correct. Okay, all those 3, even though it is written in maths differently, but it is exactly the same. So that's maths. Okay, So that's why it's very good. So that's why I asked you to prove what is the mistakes. And if you have 3 different answers, so how do you prove that all those 3 answers or 3 impulse response HN is actually exactly the same? It doesn't look the same, but it is the same. So how do you prove that? You should be able to do that, because as an engineer, we should be able to do that. So that's why we do. That's why we become an engineer, right? So we play with maths to solve some application. So now it is on a signal. Okay, all right. So this is a second method. We're going to use a scaling in Z domain properties. So what is the properties again? The properties is, if we have this a to the power of n of hn, so we should solve not hz, but z minus that a. Okay, this a, not that power, the a in front. So let's say we have a h1n, right? Because what we have here is this one. This is a 2 to the power of n. And this is the en. So our a now is 2 to the power of n. And multiplied by hn. So that's why now try to separate that first. So we separate that. So let's say we have h1 without the 2 to the power of n. Okay, we separate that. So we just take delta n minus 1, delta n minus 2. So then again, you refer to the table number 4, right? Table number 4. Then you will get 1 plus z minus 1 plus z minus 2. So this is because this is after we separate. Now we need to combine it again. So to combine that again, so then we know that our h is actually, our hn is equals to 2 to the power of n h1n. Okay, so what is the h1n? So this one, delta n minus 1, delta n minus 2. So but now we multiply by 2 to the power of n. And we have h1z here. So to get your h z, the overall h z, we will replace with z divided by 2. Okay, why divided by 2? Because the a is 2. So then z divided by 2, so you will have this one as z to the power of minus 1, and this is 2 to the power of minus 1. And 2 to the power of minus 1 is actually 2. Okay, and then z, this one is z to the power of minus 2, and this is a 2 to the power of minus 2. So which is, you will get a 2 to the power of 2 as a denominator, and then bring it up, so you get 4. Right, so that's why you get 1 plus 2 z minus 1 plus 4 z minus 2, which is equals to this one. Right, so you can either solve it using this one, or you can solve it using scaling properties, scaling in Z domain properties. Right? Differentiation, we're not going to cover that. Conjugation, we're not going to cover that, because when you have this, so it means that what is conjugate. But it is important to know what is a conjugate. So we're not going to cover these properties here, but later you need to know what is in general, you need to know what is a conjugate. Right, and again, this is actually math, so you have to learn about because Z domain is a complex domain. Z is a complex value, and you cannot avoid when you have a complex value this term conjugate, because it's very related to complex value. Whenever you have a complex value, you can have this term conjugate. And what is a conjugate is actually quite simple and straightforward. So what is conjugate for complex number? A plus JB. So why we care about complex number? Because Z is a complex value. Z is actually real plus imaginary. So this is a this is a real. This is the B is the imaginary because there's a J here. Okay. So if we have A plus JB as one complex value, so it's conjugate, or sometimes we call it a conjugate pair. So there's a pair. For complex value, you can have a pair. So we call it as a conjugate pair. And the conjugate is actually if this is plus, so we have a plus to the imaginary value. So the conjugate is we change sign on the imaginary value. So for A plus JB, the conjugate is A minus JB. Okay, real parts, no change at all. The imaginary parts, you change the signs. Okay, so it means that this is conjugate to this one, and this one is a conjugate to this one. Okay, so that's why it's a conjugate pair. So it's conjugate pair. So just change the sign. Right, so and another one, because this is a complex number, again, complex number can also be written as, this is in polar form, we call it polar form. Okay, of course, this is, we call it a complex number, so don't make it complex, right? So we have seen complex numbers since the secondary school. So it's not that complex, actually. So it's not that complex. So we just need to know what is the form and how does it do. So what is the anatomy of the plane? So then I think everything will be fine, right? So this is even not the first time you're seeing this. Some of you is already at fourth year. So some of you is maybe still at a third year. So you have seen this, I think, more than 5 years, right? So it's not new. It's not new. So as an engineer, this is just like it's like an ABC to us. So make sure you familiar with this thing. Complex number, we can also write it as a polar form. In polar form, which is this is the radius, this is exponent to the power of j theta, right? So again, the trigonometry. So the one which is you already you start learn trigonometry again from secondary school. So that is theta. That one is the r. So this is the imaginary. This is the real part. Okay, so instead of writing it as a real plus imaginary, you can write it as a radius multiplied by the exponent of j to the power of theta. Okay, so that's the angle. And in this course, again, that theta is very, very, very important. Okay, we will see that in later chapters. Right? So that's why what is the R again? So we have discussed this just now, A squared plus B squared, or real squared plus imaginary squared square roots, which is the radius. So then the conjugate, because what is the conjugate? You change sign on the imaginary part. So which is whenever you find J, or sometimes we write it as an I, so change that sign. So if you have a REJ theta here, so what is the J? So that's the J. So you change that sign. So what is the conjugate for REJ theta? So it is a RE minus J theta. Okay, all right? So that's a complex number. And because we're not going to cover this, the properties, but you need to know what is a conjugate. So I'm going to skip this one, time reversal, skipping it. So this is our last properties that we're going to cover today. So which is a convolution. And of course, convolution is very, very important because that's the process. That's the main process that we are solving in this course. So if you look back at this diagram, so we have a system here, okay? So we have a system. So that system, we have an input, output, and the filter itself, which is the impulse response. So we are actually, to do that, to get the output, so we are actually doing convolution, right? So one of it. And if it is IIR, so you have no option. You should do difference equation. You need to solve difference equation. And we have covered this, what is a difference equation, what is a convolution, what is an impulse response, those things. So actually, these are the things that we learn in this course. Okay, so most of it is actually on convolution, on what is the filter. So what are the analysis behind it? Okay, just implementing it, we are done with implementing it. But we need to go further. We need to analyze it. Right? So to do that, so this is why one of it. So we need to understand these properties. So which is a convolution. So what is the properties on convolution? If you have a convolution between two vectors. Okay, in this case, those two vectors is these two vectors are signal. So signal 1, signal number 2. Right? It can be also, but most of the time is actually when you do this. So it is on a system. Let's say you have two systems, H1n and H2n, and then you do convolution. In time domain, the convolution becomes multiplication. Okay, then this is one of the purpose why we do Z transform, because doing convolutions is actually not as easy as doing multiplication, the maths. Okay, so when we do the design, when we do a solution, so actually doing multiplication is much easier than convolution. So that's why this is very important. So this is very important. So that's why we learn a Z transform. Right? So let's see one example here. So let's say xn is equals to un. Find yn, which is yn, the convolution between xn and x minus n. Okay, so this is a time reversal. I didn't cover this one, but let's just assume that we have xn after doing this convolution. So we get 1 over 1 minus z to the power of minus 1, and x minus n. So we get 1 over 1 minus z. Okay, so those are the two results of the Z transform. And to get a YZ, so it will be very easy because we doesn't have to do the convolution, because a convolution to an FIR is easy. But if you have a system which is on IIR, so actually you cannot do the convolution. So even though the equation theoretically can be written as a convolution. So that's why solving it in a Z domain is much easier. So then we have a YZ equals to just multiply these two. So you just multiply these two. Okay. So why it is not possible to do convolution for IIR? Anyone remember? Anyone remember? Why can't we do convolution for IIR? So let's see.
Because it's infinite.
Because it is infinity. Okay. Because it has an infinite length. So how can you multiply, and then you need to sum everything. So for an infinity number of samples, so that's not possible, because when you do multiplication, you do the process in your computer, right? When you do the process, where should it be? On RAM or on ROM?
On RAM.
On RAM. So it's not possible to have an infinity memory of your RAM. Okay, you cannot have that. So it's not possible. Even the ROM, it doesn't have an infinity number of a memory. So that is not possible. It's not possible. So that's why when we do it in a Z domain, so it is just some multiplication, something like this. So it is quite easy to solve it. After we do everything, the solution, then we convert it back. We inverse it back into time domain later. Okay, we will see that later. We will see that kind of a process many times later, because that's how we solve the system. But for now, we just need to know that a convolution in time domain is actually just a multiplication in Z domain. So everything becomes simple. Okay, I'm going to leave this example for you to look at it and then try to understand it. But if you doesn't understand any part of it, you can always ask me. right? So then, okay, so we're going to stop there. So we're not going to cover this initial value theorem. Okay, done. All right, so, and again, the bonus mark is still open. Okay, the bonus mark is still open, and I'm giving a hint just now. There's a mistake relating to the delta n. Okay, so try to find it, try to understand it, fix it, and then try to give a new answer, right? And the other one is what is the question? Those not accurate answer, which is from Connie and Jason. So try to prove it why it is not correct compared to Ziad answer. So Ziad answer is correct, so but those are not correct. So how do you prove that? So how do you prove that? Because how do we know Ziad's answer is correct? It's just I'm saying that it is correct. So you shouldn't stop there, right? So because I might be wrong. So there must be some methods on how to prove those answer is actually wrong and that answer is actually correct. Okay, so try that so that you might get a bonus mark. All right, so if any question, last call, any questions?
Doctor, I would like to confirm, is there really three correct different answers for the quiz?
Yes, I already tried. At least there are three. At least there are three. And possible to have more than that. Okay. So try it. So okay, if you can understand it. So that's why it's very interesting on maths because even this is a maths on engineering. All right. So we can have many solutions, even though the end product is not looks the same, but it is exactly the same. It is exactly the same. All right, try it. It is confirmed. At least three. Might be more. Okay, any other question? Any other questions? And just a reminder, next week is our test on Thursday, okay, in class time. All right, I think no more questions now, so we will end this class at this point. So we will go for the next chapter next week. All right. So Assalamualaikum warahmatullahi wabarakatuh and good morning, everybody. See you next time.
Thank you, Doctor.
The test cover is up to week 4. Okay, so today this week is week 5. So inverse Z transform is not covered, right? So it's up to the last week until pole and 0. Okay, so that's chapter 1 and until chapter 4. All right. Okay. Bye, everybody.
Thank you, Doctor.